Deploying automated machine learning for computer vision projects, a brief introduction for endoscopists. Disclaimer. These are our disclosures. These are the keywords for this project. Here is a review of some relevant terminology. Hyperparameters are user-specified values that control the model training process, and tuning is the process of selecting the optimal hyperparameters for a given architecture. This article focuses on the object detection and classification tasks, which find the location and the label of an object, respectively. Artificial intelligence and machine learning will play a growing role in gastroenterology. Computer-aided polyp detection is an early example of how these AI and ML technologies can be applied to clinical practice. Gastroenterologists have an opportunity to learn basic ML skills in order to engage with this rapidly evolving technology. Automated ML platforms simplify or automate some of the key engineering steps of machine learning to make ML more accessible to a large range of users. AutoML aligns with the no-code movement, which aims to create intuitive user interfaces to democratize computer programming. Standard machine learning workflows typically require complex decisions around how an algorithm will learn while training on the dataset. These decisions involve choosing the number of nodes, layers, and the balance of training versus test data, all of which are examples of hyperparameters. AutoML platforms determine the best model by optimizing the architecture and hyperparameters automatically. AutoML may be a useful tool for endoscopists and researchers to build models that can be applied to endoscopic images. While the machine learning is done by the AutoML platform, data processing must be done by the user, and therefore certain prerequisite computer skills are still necessary, including familiarity with Python, which is the most common language for ML projects. Jupyter Notebook is a very useful tool that allows you to edit and run local files in your browser. If you're using the Sun dataset, the scripts provided can be run in your Jupyter Notebook to create the import files. Otherwise, they can be used as templates that can be modified for your dataset. In order to manipulate the data, it is recommended that you have a basic understanding of how to use NumPy and edit CSV files using Python. A great tutorial on Python and NumPy is included in the supplementary materials. The Sun dataset contains image frames from 100 colonoscopies with over 150,000 annotated polyp and non-polyp images. The annotation files for the data contain the bounding box and pathology of each polyp. The Sun dataset has been made freely available by the research team led by Dr. Mori. The link to the dataset is included in the supplementary materials of the attached manuscript. In order to use the Google AutoML platform, the annotation CSV needs to be reformatted using minimal parsing. The code for the parsing is included in the supplementary materials. To use Google AutoML, first create a Google Cloud account and a Google Storage bucket, which is similar to a file folder to store data. Next, the images can be uploaded using the Google Cloud Shell Software Development Kit, or SDK, which provides an easy way to upload large datasets. The gsutil command shown on screen right now copies the entire folder and its contents into our Google Storage bucket. We then use a simple Python script to generate the import file, which will associate the correct label with each image and generate the dataset that will be used for the model training. We first create a name for our dataset. Next, we choose what task we are interested in. In this case, it is object detection. We then provide our import file so that Google can associate bounding boxes and labels with each of the images. An email is sent to your account once this is finished. After successful importation of the data into the AutoML platform, we then set the parameters for the model we want to create, including the maximum number of node hours, a measure of computer resources you want to train the model with. A reasonable starting point for this value is 20 node hours for object detection and 15 node hours for image classification. The model will train on Google servers and an email will be sent to your account once training is finished. These are the results for our polyp detection model. We see the precision recall curves, which illustrate the trade-offs between eliminating false positives and false negatives. The curve helps the user find the confidence threshold that will maximize precision and recall. For this model, the default confidence threshold of 0.5 does not yield the best trade-off, because the precision is very high while the recall is more than 10 points lower. Therefore, we manually adjust it to a confidence threshold of 0.32. This adjustment increases the F1 score, a measure of accuracy that balances precision and recall, from 0.94 to 0.965. The user interface also gives examples of false negatives, false positives, and true positives. These examples can be used to improve your model. For example, if you see a lot of false negatives or positives in a particular region of the colon, more images from that region could be added to the dataset to improve the model. The CAD-E model trained using Google AutoML had an average precision of 0.789. The precision at an intersection over union threshold of 0.3 is 0.977 compared to 0.997 for a purpose-built model based on the Sun dataset. In general, the higher the IOU threshold, the lower the precision because the predicted and actual bounding blocks need to overlap more for an image to be considered a true positive. The average precision in this context is the average of all the precisions when the model is evaluated across all intersection over union thresholds. Google AutoML also allows you to make models to predict the label of an image. For our project, we created a classification model to predict the pathology of a polyp in the image. The results for this model are presented here. Google automatically generates a confusion matrix for your model based on performance with the test data. A confusion matrix indicates how often the model predicts the correct label and the most common incorrect label predictions for each class. Again, we see the false negative, false positives, and true positives for each of the classes recognized by our model. This information can help you evaluate strengths and weaknesses of your dataset. Google AutoML can be a useful tool for rapidly prototyping computer vision models for gastroenterologists, and may be a useful entry point as a project to learn basic ML skills, which can be applied to computer vision projects in GI endoscopy. While the AutoML tools reviewed here are currently only usable on still images, future iterations of these technologies will allow users to develop and deploy similar tools on live video.